All right, what is going on, everybody? This is just going to be me working out a couple of problems from the review sheet. The keys should be going up later today, so you can actually see what all the correct answers are there. But I wanted to work out a couple of example problems just because I had some questions from a couple people asking about them. So what we're gonna do is we're gonna do number 6A, and then you might not have noticed, you might not have, I don't know, but I the numbering screwed up. It went from like 1 2 3 4 5 6 and then 4 5 6, and then it went like numbered from there from the rest of it. So I'm gonna do number 6A, and then after the numbering screw up, I'm gonna do number 4 and number 12. That's gonna give a Raoult's law, that's going to give a boiling point, freezing point question, and that's going to give a net ionic equation. Those are probably like the three major things that we kind of talked about this chapter. So first, for number 6A, it says that you have silver 1 nitrate and sodium chloride. First thing we obviously have to do is we have to translate these. So silver 1, silver is Ag with a 1 plus charge. Nitrate is NO3 with a 1 minus charge. Sodium is Na with a 1 plus charge. Chloride is Cl with a 1 minus charge. Across all of our charges, we don't need to actually do any subscripts. They will all just balance out by themselves. And then we're going to go ahead and write them down. This would have been on the line for molecular equation. So for molecular equation, we've got Ag in O3. I'll put my little parentheses. Now if I go to my solubility rules, which I have over here to the side, one thing that I've noticed some people making mistakes on whenever I check to the worksheet for this is that some people were jumping right to the bottom and seeing, oh, okay, well, like there's something down here, so it just must be insoluble. The order they're listed in is not entirely important. You don't have to only follow them from that order, but it's probably for the best that you consider them in order from number 1 and then down to number 5. So let's start with the first thing. Does this contain a group 1 cation or ammonium? Now, important to note that I added somewhere on one of the earlier slides or earlier logs, but group 1 includes hydrogen. I know it's kind of weird. This is like the first time that hydrogen actually gets to be a part of group 1. Usually it's like its own thing, but it is actually a part of group 1 in this case. That's because acids are all soluble in water. But Ag is not group 1. This is not a group 1 cation or ammonium. Number 2, does it contain acetate or nitrate? And in this case, it contains nitrate. Notice it says regardless of cation. So even though silver is a common exception down here, all we care about is that it's nitrate. And because it's nitrate, it's going to be aqueous, AQ. Okay, next one is NaCl. Now this one you should just know, because you just know that you can do this. But just in case, does it contain a group 1 cation or ammonium? Yes, Na is in group 1, so that is aqueous. And because they are both aqueous, that means that we are going to continue. If either one of these were a solid, we would just stop. There would be no other way for us to do the reaction. So we're going to switch. We've got AgCl. Now for AgCl, does not contain a group 1 cation or ammonium, does not contain acetate or nitrate, does contain a halogen, but this says all salts containing a halogen are soluble except those that contain silver, lead, or mercury 1. And in this case, Ag is silver, so that means this one must be a solid. And then our other combination is going to be NaNO3. That contains both a nitrate and a sodium, so that is definitely aqueous. To balance this equation, they're actually just all going to be 1s. There's nothing crazy to balance for this one. Now, we would have to do our splitting apart. I'm going to rush through that because I assume that if you are struggling, that is probably not the part you're actually struggling with. So I'm going to go through this just a little bit quickly. So we've got complete ionic equation is going to be Ag plus AQ plus NO3 minus AQ plus Na plus AQ plus Cl minus AQ arrow AgCl solid plus Na plus Aq plus Cl minus Aq. Or sorry, NO3. Try to go too fast. NO3 minus Aq. Now if we look through and find all the pieces that are the same on both sides, I'm going to use a pencil to cross them out. We've got a Na plus Aq and an Na plus Aq. We've got an NO3 minus Aq. We've got an NO3 minus Aq. The only thing that's left are these three pieces. So our net ionic equation, getting rid of all the stuff that doesn't actually change throughout the reaction, is Ag plus Aq plus Cl minus Aq gives you AgCl solid. The biggest mistake I noticed people making was, like I said, people would see things like sodium carbonate, potassium phosphate, lithium hydroxide, and all of those, because they have group 1s, you don't have to look at this. Like it says here, all those except those mentioned in Rule 1. So if these are paired with anything from group 1 or with a hydrogen, they actually are just fine. They will dissolve in water. The other common thing that I saw people kind of forgetting or messing up on, as I just realized I'm pointing, not on screen. So yeah, people would see these things with group 1, and they would just assume that means that it's insoluble. But group 1 overrides. Group 1 is just, they will always dissociate. They will always split down and split apart in water. The other one is just people are missing this common exception down here. You do have to know and have to use this exception. The calcium hydroxide is soluble. You actually need that for the last question on the worksheet, number 19. But we're going to go ahead. We have two other problems that I want to do. This one's going to be a boiling point elevation, freezing point depression. So this is it's not technically number 4, but the short answer number 4. But if you flip over to the page, it's a solution containing 50 grams of glucose question. So that question says, as I started reading a second ago, a solution has 50.00 grams of glucose, which is, just in case you're not familiar, C6H12O6, and it's in 425 grams of H2O. So 425 grams of water. And then we want to know molality, almost said A, 2, and 3. For B, we want to know freezing point. And C, we want to know boiling point. Hopefully my pen lasts long enough that I can actually get through this problem. Okay, first of all, molality. So A, molality is moles of solute per, come on pen, you can do it, kilograms of solvent. We don't have either of those numbers. Now, for kilograms of solvent, we can just do 425 grams, because H2O is our solvent, because there's more of it, divided by, there is 1,000 grams in 1 kilogram. So 0.425 kilograms of water. Now, for moles of solute, however, we're going to have to do a conversion. And that conversion, sorry, tilting the paper. That conversion is going to be 50 grams of glucose. We started with 50 grams. And then we're going to need to do a gram to mole. Now, I actually believe I tell you the molar mass of glucose in a later problem. And that molar mass of glucose is 180. I think I used 0.2 there, but if you look on the periodic table, it'll actually be 0.18. And that's what I used for this one. But 180.2 should give you a close enough answer. And that's per 1 mole. If we multiply that out, we get 50 divided by 180.18. We get 0.27750027775, which is a very nice symmetrical number. So 0.27750027775. Again, you don't have to write the full thing, but I'm actually going to be just plugging that number in directly. So I'm going to use that full value for this. So now I'm going to take this number. Sorry, that's moles, not molal, not molal. It's It's been a long week, guys. Okay, so that's our moles of solute. Now we're just going to take this number and divide it by our 0.425 kilograms. So 0.2775 divided by, and again, I'm actually just going to carry over this whole number. I'm writing this just because I don't want to have to rewrite this entire number a second time. Over 0.425 kilograms. And if you plug that into your calculator, I believe you should get 0.6529418 molal. Which, because it does want an answer, we are going to round to sig figs. 425 is 3, 50.00 is 4, so we're going to go to 3 sig figs. So we get 0.653 molal. Now, you can use this number for the later problems, but I'm actually going to carry over this entire number this entire number over here into all my future calculations, just for, making sure that I've got it as precise as I can possibly get it. Okay, so for part B and for part C, we can actually do both of these kind of at the same time. The general formula is change in temperature equals KMI. Or, as I like to say, because it kind of rhymes, delta T equals K me. Now, K is different depending on what you're looking at. So in B, I just realized in the problem it says A, C, and D. Man, I was just way off for all this. But a C is going to be 1 point in the worksheet. It's actually the second one, so it's going to be B on here. So we've got 1.86 degrees Celsius per M, and that's because that is the freezing point, and this one's going to be the boiling point. Boiling point is 0.51, but all the rest of the pieces are the same. We have molality. I is Van't Hoff factor, and if you remember, the way you calculate Van't Hoff factor is you determine how many pieces your substance in question is going to split into. In this case, it's glucose. Glucose is made out of all non-metals, and it's not an acid. There's no H out front. That means that it's molecular, and that means that our I is going to equal 1 because it's molecular. So for B and for C, or for our freezing point and our boiling point, we're going to basically set them up the same way. My K in the top one is 1.86. My K in the bottom one is 0.51. Our M is 0.653. And our I is 1. And now, plugging all of those into your calculator, you should get, if I did it correctly, which I might not have, but I believe I did, you should get 1.2143. And then for our boiling point, you should get 0.3327 or 2979. Which, I mean, those aren't our actual real answers to this question anyway. These are just the delta T's. We want to know our actual freezing point and our actually boiling point. So our actual freezing point would be if it started at 0 and freezing point depresses, so freezing point goes down, we would subtract 0 minus this number. Of course, we would need to make sure that we go to the correct number of decimal places / sig figs, so it would actually be negative 1.21 degrees Celsius. That's our new freezing point. And then our normal boiling point is 100. This is boiling point elevation, so it's going up. And since it's going up, we're going to add this number to our 100 degrees. So our new boiling point is 100.333 degrees Celsius. Now notice this has a way bigger amount of sig figs than this number. But this number here, we rounded it to 3 sig figs, which was 0.333. And then we did an addition problem where we added it to 100, which is an exact amount. So even though it looks like, well, man, this number is going way further decimal place-wise, it is still technically the correct number of sig figs. So it is actually our correct answer to this question. Okay, I hope that helps with a boiling point elevation, freezing point depression question. For a lot of the other ones, they just get difficult because they involve like doing some algebra where you have to rearrange. For our last one that we're gonna do number 12 after the screw up. So this is the one that I also screwed up for some reason in my formatting, and it didn't give you enough space. It was really cramped in there. So I assume most of you probably just wouldn't actually even have the space to work it out in the space I give you on the worksheet. You don't need much, but you need like more than the 2 lines I gave you. So I'm actually going to work it out in the rest of the space. I did switch to a different pen though because I feel like I'm not trusting this purple to last the rest of the time. So our question states, calculate, so find pressure made from 456 grams of glucose dissolved into 892 milliliters of water at 20 degrees Celsius. Assume the density is 1.00 grams per milliliter. And that's just the normal density of water. I've mentioned that in class, I believe, a couple times, but this is just the density that water has. 1 milliliter of water weighs approximately 1 gram. Now, our formula we're going to use for this is called Raoult's law. Raoult's law states that the pressure of a solvent is equal to the mole fraction of, oh my god, this pen's wanting to die too, of that solvent times the initial pressure of that solvent. So if you know what it originally has a pressure of, and you know its mole fraction, you can determine its new pressure. And again, this is called Raoult's law. So for our P naught, or our initial pressure, you know what, we're gonna switch to our my trusty never runs out pen, but that's way too dark. Okay, P naught. We just go and look at the chart. Remember, this is on the back of your solubility rules sheet. So it tells us it's 20 degrees Celsius on the back of my solubility sheet. I find 20 degrees Celsius and I go over, and you get 17.54. So 17.54, and it's mmHg, which is just millimeters of mercury. Now, for our mole fraction X, to get mole fractions, you need your moles of a substance, whatever it is you're caring about, divided by the total moles. And then this one's not made into a percentage. It'll stay as a decimal. So we're just going to have to convert both of the things that we have into moles. So glucose, we're going to do 456 grams. And it actually told us the conversion factor. It tells us in the problem, we can use 180 point. I'm going to use 1.8 again, but 180.2 is what it tells you in the problem per 1 mole. And then for water, we have 892 milliliters. And then we can go, okay, well, in every 1 milliliter, we have 1 gram. And then in 18.02 grams, we have 1 mole. Now, I know I'm getting kind of cramped on space, but now I'm just, going to be stubborn and not want to switch pages. So let's go ahead and figure out what these are in our calculator. So we've got 456 divided by 180.18. So we get we'll do 2.531. And then for our other one, 892 divided by 18.02, we get a mass of 49.501. Well, we'll go ahead and go that far for that one. Okay, and now we have all we need. So our pressure of our solvent is equal to, and hopefully this doesn't smear. This is the reason I wasn't using this pen in the first place. We're going to do of our solvent. Remember, I know that I screwed it up in the notes originally, but we want the mole fraction of the solvent in this case. So we're going to put our 49.501 divided by 49.501 plus the 2.531. So 49.501 divided by, in parentheses, 49.501 plus 2.531. So it's just adding these two numbers together to get me total moles. And then I just multiply this number by my initial pressure, 17.54. And that will give you the new pressure. So let's go ahead and plug it in. So 49.501 divided by 49.501 plus 2.531. Multiply that by 17.54. Notice this was my mole fraction, which makes sense because it's a number less than 1. But if I multiply that, that will give me my new pressure, which is 16.686799, which obviously we care about sig figs. In this case, the question, looking back to just double check, we got 456, 892, 20.0, and 1.00. That's all 3 sig figs. So we've got a pressure of 16.7 mmHg. Okay, if you come up with any other questions that you think I can answer, please send me an email or write them in the box to the side. I still haven't fully fleshed out the test that I'm going to give you guys on Monday. I think it's going to be 1 to 3 short answer questions and then 1 to 2 calculations is kind of what I'm going for. And then probably a net ionic in there. So I haven't fully figured it out. It's going to be a lot shorter than our normal tests, but it's probably going to be a little bit more thought-provoking and test your critical thinking and kind of your other skills than just being able to kind of regurgitate the formulas, since I know you would be able to just have like a piece of paper in front of you, and I have no power to stop that. So hope you guys have a great rest of your day. I hope you guys have a great weekend and you enjoy this lovely weather, and I hope to see/hear from you soon.